In this lesson, we're going to discuss the world of application security. Application security is a critical aspect of software development that focuses on building applications that are secure by design. By utilizing application security, implement measures to prevent, detect, and remediate security vulnerabilities. There are 6 main areas we need to look at in terms of application security, including input validation, secure cookies, static code analysis, dynamic code analysis, code signing, and sandboxing. First, we have input validation. Input validation is a fundamental aspect of application security that acts as a gatekeeper to ensure that applications only act on well-defined and uncontaminated data. Input validation is focused on directly countering various forms of attacks aimed at exploiting data input vulnerabilities to preserve the integrity and behavior of the application. In the vast and complex world of software, where interactions are multifaceted and unlimited, the need to authenticate, clean, and secure data inputs cannot be overstated. Whether it's a user who fills out a form, data is transferred from one application to another, or an internal function calls another within a system, these are all considered inputs and must be properly validated before the application performs any kind of operation using the user-provided data. Each of these types of data being input will represent a point of interaction as well as potential vulnerability to our systems. Often, threat actors will attempt to break into a system by feeding it data that could trigger an unintended reaction or breach by conducting a SQL injection, cross-site scripting, buffer overflow, and other types of attacks. This is why input validation is important, because it serves as a kind of quality control for data to ensure that every piece of information is valid, secure, and correctly formatted before it's processed by the application. This is not just about preventing malicious attacks, but it also helps to ensure that our systems behave predictably and can handle errors gracefully. For example, if a function expects a numerical value but receives a string instead, it could cause errors or unpredictable behavior. Proper input validation catches such issues before the application attempts to perform an operation on the wrong type of data. Implementing input validation involves establishing specific criteria known as validation rules. These rules delineate acceptable and unacceptable inputs. For instance, if an input field is expecting a phone number and the validation rules might require 10 digits and no letters, special characters, or additional digits. Anything outside of this would be flagged and rejected, or the system might request the user to input the data again. These rules can be very simple, like checking if input is empty, or more complex, like verifying if the input matches a regular expression used by an email address. However, input validation is not just about setting up boundaries, but it is also an important security measure to ensure that data is validated early in the process. We refer to this as front-end validation, where any web forms created in an application will ensure that the data matches the right format before accepting it. Conversely, we will also implement back-end validation as well to ensure that our servers check the data prior to allowing an application to utilize that data. It is important because front-end validation alone can be bypassed by an attacker, but using back-end validation by itself could become more expensive or time-consuming since it relies on your own servers to do the validation. Now, while input validation is critical to perform, it is important to remember that it's not a cure-all solution, and you still need to have a multi-layered approach to security known as defense in depth to achieve high levels of security. This might include using secure communication protocols, regular security auditing, and implementing proper error handling to implement your own defense in-depth strategy. Next, let's discuss the use of secure cookies. Cookies are small pieces of data stored on a user's computer by the web browser while browsing a website. They are used to maintain stateful information between the web server and the client. However, if not properly secured, cookies can be exploited to hijack user sessions or steal sensitive data. Secure cookies are a solution to this problem. They are transmitted over a secure HTTPS connection to prevent potential eavesdroppers from intercepting the cookie data. For example, a banking website would use secure cookies to store session information to ensure that even if an attacker can intercept network traffic, they cannot read or modify the cookie data. There are some practices that you should be aware of when utilizing cookies. You should always refrain from utilizing persistent cookies for session verification. Instead, you should always generate a fresh cookie each time the user authenticates again to prevent session hijacking from occurring. Also, you should enable the secure attribute on the cookie to ensure that a cookie is not transmitted over an insecure HTTP connection accidentally. To protect your cookies from being reachable within a document object model or by a client-side script, you should enable the HTTP only attribute in the cookie itself. If you need to control which origin can access a given cookie, you can configure the same site attribute on the cookie so that it reduces the risk of a cross-site request forgery attack from being successful. Next on our list is static code analysis. Static code analysis, also known as static application security testing or SAST, is a method of debugging an application by reviewing and examining its source code before the program is ever ran. Static code analysis is designed to analyze source code for potential vulnerabilities such as buffer overflows, SQL injection, and cross-site scripting attacks, as well as ensure that the programmers have implemented proper input validation into the front end and back end of the code. For example, a static code analysis tool might flag a piece of code that concatenates a user-provided string into a SQL query. This could potentially lead to an SQL injection vulnerability if the user-provided string contains a malicious SQL command. Instead, the program should perform input validation on the user entered string before passing it to the SQL database server. Alternatively, you could code the program so that it only utilizes templated queries instead of allowing for a direct input of a search term by the user to prevent security issues. Static code analysis is usually performed using software analyzers. The analysis software must support the programming language used by the source code. Now, if you perform this code review using a human instead of a static software analysis tool, we refer to this as manual code review. When conducting manual code reviews, we usually assign a different programmer to review the code than the person who initially wrote the code. Also, it helps us find any mistaken assumptions or uncover any lack of knowledge or experience that the initial programmer may have had. Next, we can also utilize dynamic code analysis to find additional vulnerabilities in our applications. A dynamic code analysis, also known as a dynamic application security testing or DAST, is a testing method that analyzes an application while it's running. Dynamic code analysis is designed to find vulnerabilities that a static code analysis might miss, such as runtime errors and memory leaks. A dynamic code analysis tool might interact with a web application to provide various inputs and observe the related outputs to identify any potential vulnerabilities. For example, if the tool inputs a script into a form field and the application returns the script in its response without proper encoding, this could indicate a potential cross-site scripting vulnerability. When it comes to dynamic code analysis, the two most common methods of conducting dynamic code analysis is fuzzing and stress testing. Fuzzing, also known as fuzz testing, is a software testing technique used to discover coding errors and security loopholes in software, operating systems, or networks by inputting massive amounts of random data called fuzz to the system in an attempt to make it crash. The process of fuzzing involves the automated injection of malformed or unexpected data into the system and then monitoring for exceptions such as crashes, failing built-in code assertions, or potential memory leaks. Stress testing is a type of software testing that evaluates the stability and reliability of a system under extreme conditions. The goal of stress testing is to identify the system's weak points and determine how it behaves under intense loads and how it recovers from failure. For example, a website might be stress tested by simulating thousands or millions of users accessing the site simultaneously. This can help identify bottlenecks in the system, test the effectiveness of load balancing, and ensure that the system can handle high traffic volumes. All right, now that we have discussed some different code analysis techniques, let's discuss a way that a programmer can attest to the fact that they wrote a specific application. To do this, we utilize code signing. Code signing is a technique used to confirm the identity of the software author and guarantee that the code has not been altered or corrupted since it was signed. Code signing involves using a digital signature to authenticate the software's source and integrity. Code signing is the main way to confirm that a piece of code, like a program or script, is genuine and hasn't been tampered with since it was distributed by the developers. The process works by having the developer make a unique code called a cryptographic hash of the file and then encrypting that hash using the developer's own private key to create a digital signature of the program's file. Whenever the program is sent out next, it will come with a copy of the developer's code signing certificate. This certificate has a public key that the receiving computer uses to check and confirm that the signature is valid. Then the operating system asks the user to decide if they trust the signature and want to run and install the given program. For example, when you download an application from the Apple App Store, you can be confident that the application is genuine and hasn't been tampered with since it was uploaded by the developer. This is because Apple requires all applications to be signed with a developer certificate before they can publish it to the App Store. It is crucial to understand that the process of digital signatures on a file or program does not guarantee its absolute security or the absence of vulnerabilities. However, what it does ensure is that the file or program has not been tampered with since the developer originally created and signed it. In other words, the digital signature confirms that the file is in the same state that the developer intended it to be when they distributed it. Finally, let's talk about sandboxing. Sandboxing is a security mechanism that is used to isolate running programs by limiting the resources that they can access and the changes that they can make to a system. Sandboxing is a method of executing untested or untrusted programs without risking harm to the host device or network. For example, when you open a potential harmful website in your browser, the browser runs the website's code in a sandbox. This means that even if the website tries to execute malicious code, it won't be able to affect your entire computer because it's confined to the web browser's sandbox in most cases. These sandboxes provide a more comprehensive solution than a typical anti-malware tool would, since they allow for testing code under various environments and not just the current system configuration, since you can run numerous sandboxes on one system using different operating systems. For example, if I am running a macOS on my MacBook Pro, I can also run a sandbox that contains macOS as its operating system, as well as sandboxes with that Linux operating system or a Windows operating system as well. So remember, in the world of application security, we need to consider 6 key areas: input validation, secure cookies, static code analysis, dynamic code analysis, code signing, and sandboxing. Input validation is designed to act as a vigilant gatekeeper that ensures that our applications only process well-defined and untainted data to counteract various forms of attacks. Secure cookies help to prevent vulnerabilities like session hijacking through the secure transmission and using the proper attribute settings on the cookies. Static code analysis involves proactive vulnerability detection through source code review. Dynamic code analysis is used to uncover any runtime issues. Code signing provides a means to verify the software authenticity, and sandboxing is used to isolate any untrusted code to mitigate its ability to potentially cause harm. These multifaceted security measures, when integrated into software development practices, help to create a robust defense strategy against the ever-evolving world of cybersecurity threats.